Today we're going to be having Neekon from MIT talking about how continuous CLWE is a part of CLWE.
All right, thanks so much. So as you said, my name is Neekon, and this is joint work with my wonderful collaborators, Aparna Gupta and my advisor, Vinod Vaikuntanathan. Okay, so let me give a brief outline of what I'll be talking about today. So first, I'll introduce the learning with errors assumption, which has been ubiquitous in cryptography. Then I'll talk about a related notion called continuous LWE that has been recently defined. Then I'll talk about the connections between continuous learning with errors and learning Gaussian mixture models, and I'll define what that means. Then I'll talk about one of our main results, a reduction from LWE to CLWE. And lastly, I'll give some other applications of CLWE and what our reduction says about these other applications. But yeah, feel free to interrupt me at any time with questions in case anything's unclear. Very happy to take. Okay, so let's start off with learning with errors. So let Z sub Q denote the set of integers, mod Q. And we're going to let N of mu sigma squared denote the Gaussian distribution or the normal distribution with mean mu and standard deviation sigma. So the LWE assumption can be stated as follows. It's a hardness assumption. It says that if we sample a vector S uniformly at random from ZQ to the N, so N coordinates, each of which is independently uniform over ZQ, and I might refer to this as the secret vector, sort of borrowing the language from cryptography. And then we're going to generate N samples as follows. So each vector A sub I is also going to be uniformly at randomly drawn from ZQ to the N, same distribution. And then we're going to consider some noise, E sub I, drawn from the Gaussian with mean mu and standard deviation sigma. And we're going to consider these noisy inner products. So you're given these vectors A sub I, and then you're given noisy inner products of A sub I with the secret S, with this little bit of noise, and you're going to consider it mod Q. And just hopefully make the syntax clear that this, the second component here is a real number mod Q. So think of it as real numbers, interval from 0 to Q, except you have wraparound when you get to Q and you go back to 0. So the learning with errors assumption says that this distribution is computationally indistinguishable from AI along with now independent, uniformly random BI as real numbers mod Q. Yeah, and this notation here just means that the left-hand side and the right-hand side distributions should be hard to distinguish by efficient algorithms. So I'm being a little bit vague, but intentionally so. But yeah, if any of the notation's unclear, feel free to ask and happy to answer any. Okay, so why care about this assumption? Well, in particular, it's led to many post-quantum cryptographic primitives, public key encryption, fully homomorphic encryption, and truly lots more that I can't even begin to list off. And in particular, lattice-based constructions of cryptography are central to the National Institute of Standards and Technology's efforts to standardize post-quantum crypto. But furthermore, not only does it enable post-quantum crypto, that is like classical cryptography that's secure against quantum adversaries, but it also enables quantum cryptography. For example, classically verifying quantum computation or producing certifiable randomness from an untrusted quantum source. And all these applications are great, but why should we believe LWE? Like, what's our evidence for believing this average case hardness assumption? Well, for one, there's been a lot of cryptanalytic effort to break LWE because it's being considered for standardization. And thankfully, there hasn't been too much efforts to thwart this, or thankfully there hasn't been too much success in breaking LWE. But more formally, there have been reductions from worst case lattice problems to LWE, which is fundamentally an average case problem. So now to believe this average case hardness assumption, all you have to believe is that certain lattice problems are hard in the worst case. And depending on the reduction, either hard for quantum algorithms or classical algorithms in the worst place. Okay, so now let me shift gears and talk about continuous LWE, which is recently defined by Bruna, Regev, Song, and Tang. It's going to be quite similar in definition to what I just gave for LWE, except that the distributions on the secret vector S and these vectors A sub I are going to be from sort of more natural-looking continuous distributions as opposed to discrete ones. So on the left-hand side here, I've just copied over LWE, exactly the same as before. I've shifted things down by a factor of q, but it really doesn't make any difference. So I'm just scaling things down. So things are now mod 1 instead of mod q. And now let me define CLWE. So let S to the n minus 1 be the unit sphere in Rn. So the set of all vectors in Rn that have a norm, L2 norm equal to 1. And there's just the sphere within in n dimensions. Now our secret's going to be drawn from a scaled up unit sphere, where the scaling is given by a certain parameter gamma that I'll try to motivate in a little bit. And these vectors a sub I are now going to be drawn from a multivariate Gaussian distribution. So now these a sub i's are going to have mean vector of the all zeros vector and covariance matrix the identity, which you could think of as saying there are n coordinates, each of which is independently drawn from a standard Gaussian. So mean 0, standard deviation 1 Gaussian, and coordinates, each of which is independent. And the rest of the assumption is exactly the same. Exact same syntax, same noise, same everything, same assumption. So really the differences here are the distribution on the secrets and the distribution on the vectors a sub I.
Is there a reason why you draw S from the sphere as opposed to another Gaussian?
It's useful in these reductions to have the norm of it being fixed. You probably could define it from a Gaussian, and reasonable things will probably still be true. But yeah, that's a good question.
Can you say a bit about trivial regimes when what kind of gamma will make this broken and what kind of data?
Good. Yeah. So I'll motivate a little bit this later on, but gamma here. Yeah, so I guess there's essentially the best known algorithm for CLWE runs in time 2 to the gamma squared. So for gamma being root n, which is the standard setting of CLWE, there is an exponential time algorithm known. And if you scale gamma down, you're gonna get better sub-exponential time algorithms. Beta, certainly if beta is 0, the authors show you can run LLL if there's just no noise. LLL works, and even if it's I think exponentially small noise, I think LLL will also work. But yeah, I guess. Yeah.
Well, on the left, AI seems to be from has each entity has a value like 0 to 1. Right? So why it seems more reasonable to sample AI from 0 to 1 on the right as well?
I see. I mean, if standard deviation 1, I guess it's not technically the support is the whole real numbers, but it's going to be reasonably close to each entry is going to be reasonably close to 0. But yeah, I guess like there's no it's not like standard deviation Q or anything like that. It's standard deviation 1. Yeah.
The first defining computational indistinguishability, what's the meaning of giving real numbers to the public?
Okay, yeah, I guess yeah, there are a couple. I guess there are a couple ways to sort of deal with real numbers. One is to sort of work in some real model of computation, where you're given real numbers and you can work with them. The other is that really you can talk about bits of precision and you can work with that all the way through. Yeah, to a certain precision, you can work with things.
Might it make a difference to the security? How exactly you round it up?
Probably not. I mean, the magnitude of like E sub I is going to be like like roughly inverse polynomial. You could think of it. So just a logarithmic number of bits of precision, like rounding and smudging aren't going to be too different at that level. Yeah.
What do you think of the number of settings? Yeah.
Okay. Yeah. Good. So you can think of M as being really pretty flexible. But certainly you want to think of it, at least in the LWE setting, as being at least like n log q or something like that, so that the secret is sort of uniquely determined. And similarly for CLWE, you want to think of it definitely as being super linear in n, but potentially even like sub-exponentially big in n. Say that again?
Public gets easier.
Right, but we like for LWE, we don't really know good algorithms, even if m is like 2 to the root n or something.
Following up on Brian's question,
Mhm.
any real-world implementation which works with finite precision, won't there be some sort of LWE again, like exactly LWE distribution? You can multiply with the precision within the fraction n, and then the whole thing becomes like an LWE sample. Is that right?
I see. Yeah, I mean the like AI is like I guess the distributions are still going to be a little bit different. it'll now be like discrete if I'm understanding you correctly, but like these AIs are going to be roughly really close to a Gaussian now instead of really close to like uniform mod 1 or like discrete uniform mod 1. Yeah.
I mean, this is a rotationally symmetric, right?
Yeah, that's another example. Yeah. Yeah, I guess it doesn't matter too much like continuous versus discrete. Really, it's more of the distributions on it that are sort of what we want to think about here.
Yeah, this one is discrete Gaussian. This is like a continuous, but maybe rounded.
Yeah, I see. But I mean, like these A sub i's are not I guess they're uniform, discrete uniform. Yeah. No, it'll be like 0, like 1 over q, 2 over q, all the way to like q minus 1 over q. And then dimension. Yeah, so it's maybe bad notation, but it's really zq to the n, and then just scale everything down by a factor of q. So now it's mod 1 instead of mod q. Okay, let me move on. But yeah, let me give a little bit of geometric intuition for what's going on here. So here I've plotted like the CLWE distribution. So like this, the first line here. And let me explain what's going on in this colorful picture. So in the XY plane, we have these 2-dimensional Gaussian samples. These are Gaussians from a multivariate Gaussian in dimension 2. It's the XY plane. And then the color of any individual point in this plot is going to be given by whatever this noisy inner product is, mod 1, where the correspondence between numbers mod 1 and colors is given by this vertical color chart in the middle here. So I'll let you stare at this for a little bit, just so it'll hopefully make some sense. But one thing you might notice, for example, is that you have these like color bands of roughly the same color going perpendicular to the secret vector S. And that's because for the color, all you care about is the projection onto the secret vector S mod 1. So you only care about your components in that direction. So it doesn't matter if you're perpendicular. It doesn't matter what your contribution is in that direction. Okay. So why give this definition? What's the point of giving such a definition? The first is that CLWE has connections to natural like statistical learning problems. And this is what I'll talk about a good amount later on. And I should say, LWE is known to have some connections to like learning intersections of half spaces, but that's very much in the binary setting. And I urge you to think of CLWE as really fitting you into like the sort of more standard high dimensional statistics line.
Go back to the previous cycle.
Yes.
This, or the one with the plot. The plot seems to suggest that you know which direction S is once you get enough samples, right?
Why is that?
Because if you can see the bands.
Or can you see the bands? That's the, I mean,
just visually, like 2D.
Yeah.
High dimension.
Yeah, there's a graphic later on that I'll hopefully convince you that it's hard in dimension 3. But yes, it's coming later.
So is the reason that you can here basically see the secret, we have lots of samples relative to dimension, or?
Yeah, I mean, I guess that's one way to think of it. I mean, dimension 2 sort of, I guess, okay, the real intuition is that in dimension 2, how many directions are there to look at? Like, there are not that many directions. So you just like guess a few secret directions and you can see, oh, there are colors in this way. But in dimension n, there are exponentially in many n directions to look at. And it's going to be hard to like notice this color pattern. And I'll point to later on, there'll be a graphic that I'll hopefully convince you makes the problem hard in dimension 3. But sorry, it's not, I'm not here yet. Okay, so another thing we know about CLWE is that it gives rise to public key encryption. But from LWE, we know how to build a lot more crypto. So sort of the main benefit of CLWE, it seems, is that it's connections to natural statistical learning problems, which I'll mention now. So like, what problems am I talking about? One is that assuming the hardness of CLWE, one can show that it's hard to learn single periodic neurons. Neurons here in the sense of a neural network. Another application is that assuming the hardness of CLWE, one can undetectably plant backdoors in certain machine learning models in a certain sense. Another is that one can show hardness of learning noisy half spaces, assuming the hardness of CLWE. And lastly, one can show that it's hard to learn mixtures of Gaussians, assuming the hardness of CLWE. And this last one I'll focus a lot on in this talk. I will mention some of the other ones towards the end of the talk. But yeah, I'll focus on this one. Okay, so let's take a step back and think about LWE versus CLWE. So even though these problems are structurally very similar, their applications seem quite different. LWE's applications are to cryptography. CLWE's connections are to like high-dimensional statistics and learning. So are they really the same problem? Are they different? Like, are there reductions between these two problems? This was posed by Bogdanov et al. In their construction showing how to build public key crypto from it. And our short answer to this is yes. So there are reductions in effectively both directions, showing that LWE and CLWE are equivalent. And as a corollary to this, we now have a classical reduction from worst case lattice problems to CLWE. Previously, this was only known for a quantum reduction, meaning previously you had to assume the quantum worst case hardness of certain lattice problems. Now we have to assume only the classical worst case hardness of lattice problems. Another corollary is that all of the things I mentioned on the previous slide, you can now base on LWE instead of CLWE. And the benefit of this is that LWE has been extremely well studied in the cryptography community for many years. And there have been lots of tools and machinery developed for it. And you can port over some of this machinery to the world of learning. And that's exactly what we do to give some improved hardness results for these learning problems. Okay, so what is a mixture of Gaussians? Let me switch gears a little bit and talk about this problem. So I'm going to say D is a mixture of Gaussians if its density function can be written as a convex combination of multivariate Gaussian distributions. So you have these positive widths adding up to 1, and each component is a multivariate Gaussian with some mean vector and some covariance. Or another way to think of this is that with probability Wi, you're going to generate a sample from the ith component multivariate Gaussian distribution. Maybe for a picture, something like this in dimension 2, we might have a density function with each of these peaks corresponding to a different Gaussian distribution. And in fact, I want to sort of give the intuition that these things often show up in nature and in science. So for example, here's a very old example of observing some trait about like crab populations. And one thing they noticed was that there are like 2 different crab species that each of them within themselves form a Gaussian distribution over measuring some trait like size, for example. But if you only get samples from some mixture of the 2 species populations, at the global level, you're only going to observe some mixture of Gaussians. And so this model sort of shows up when you have different populations, each of which is Gaussian on its own. And what are the computational problems associated to it? Like, what is the learning problem here? The learning problem is given samples from something that we believe is a mixture of Gaussians, try to understand the underlying mixture of Gaussians that it came from. So an inference problem. And maybe the first definition you might think of is given samples from a mixture of Gaussians, try to estimate all the parameters of the mixtures of Gaussians. So try to estimate the weights, try to estimate the mean vectors, and try to estimate the covariance matrices. In this talk, we're going to talk about an even weaker goal, which is just sort of an improper learning goal, which is just going to be to output a density function that is close to the true underlying mixture of Gaussians. So this density function doesn't itself have to be a mixture of Gaussians, like your estimated density, but it still has to be close to the underlying mixture of Gaussians. Does that make sense? Okay, so
Are we primarily interested in just the computational difficulties here, not like less so statistical difficulty?
By statistical, you mean like sample complexity difficulties? I think we're interested in both. Yeah, I'll talk about what we know about this problem, both information theoretically and computationally. Yeah.
So when you say output a function, how will we output?
Oh, I guess maybe like a circuit. Say that again.
We already have sampling access. Like, is there a parametric form?
It doesn't have to be parametric, but I mean, you can think of it as like you're given some amount of samples, Then you have to output some like representation of a function, maybe like a circuit, maybe something. And after that, your sample access stops. So you're given now just a density function that's for all points, not just on the points that you're given the samples from. Yeah, so what do we know about this? So to answer your question, so information theoretically, statistically, we know how to solve this problem given polynomial in the dimension and the number of Gaussian components. So remember, G here is the number of Gaussian components in this picture. This is information theoretically solvable given polynomial samples. Yes, this is known. It's not.
I mean, the number of points.
Oh, good question. I don't know off the top of my head, I guess. Yeah, I guess. Yeah, I don't exactly know how. Yeah, I'm not sure. It's good. It's a good question. But algorithmically, so now I guess we're shifting to the algorithmic world. The algorithm is run in time n to the f of g for some f of g that's in particular bigger than g. And so this algorithm is only going to be a polynomial runtime for a constant number of Gaussian components. There are also statistical query lower bounds to this problem, showing that if your algorithm comes from a restricted statistical query model, then there's going to be a lower bound of n to the roughly order g, the number of samples you need. But what BRST show is that there's a lower bound for all algorithms, not just SQ algorithms, assuming the hardness of the CLWE problem. Okay, and let me describe what this connection is here. So here's our favorite picture of CLWE again. Let's say I like really have a color I care a lot about. Like I'm a big fan of the color red. It's a good color. And let's say I only care about the red dots here. I'm going to get some picture like this. Yeah, I only care about the ones that are red. Or more formally, I'm effectively rejection sampling on the color being close to red, or in this case, this corresponds to the inner product, mod 1, being close to 0. I'm going to get some leftover distribution like this. And this is called the homogeneous CLWE distribution because we're conditioning on it being 0 mod 1. The main observation here is that this distribution itself is a mixture of Gaussians. Like each of these little slivers you see is a Gaussian component. And so altogether, this is going to be some joint mixture of Gaussians. In particular, the mean vectors are going to be on the line spanned by the secret vector S, and they're going to be equally spaced out along this line. And the covariance matrices are all going to be the same. They're all the identity matrix, except they're like squashed in the direction spanned by the secret vector S. And a little bit more quantitatively, the number of components in this Gaussian is roughly gamma. So in the definition of CLWE, we know that the secret has norm gamma. And because we're considering things mod 1, you're going to get this periodicity every 1 over gamma in the A vectors. And so these Gaussians are going to be roughly 1 over gamma apart from each other. And so because the Gaussian has very strong tail bounds, they're only going to be essentially they're roughly going to be gamma components in your Gaussian with high probability. Yeah, good question. So I guess there's even another subtlety which is sort of thrown under the door that let me be more precise. So you can't, of course, rejection sampling on it being exactly 0, because that's probability 0, but you rejection sampling on it being close to 0 with appropriate weights, then you get this distribution. That resulting distribution is exactly a mixture of Gaussians, and there are infinitely many components in this mixture of Gaussians. What you can do is you can just truncate. Consider the distribution where you truncate the really far away Gaussian components. And then by a Gaussian tailbound, a univariate tailbound, you can say with 1 minus epsilon of the mass is root log 1 over epsilon. Yeah, far away. Yeah, exactly. So these are not degenerate Gaussians, but in one direction, it's the covariance is very small. Yeah. Okay, and formally, the computational problem associated to this distribution is to distinguish these samples from this distribution from samples from a standard Gaussian. So just a standard Gaussian versus this. And once again, someone pointed out this is kind of easy. Just look at it, right? You can see the holes. So what's the issue here? But in 3 dimensions, things get maybe a little bit more tricky. Okay, so one of these is the homogeneous CLWE distribution, and one of them is the multivariate Gaussian. All right, let's wait for it. Yeah, right there. People see that? Okay, great. Yeah, so I guess for full credit, BRST have a similar sort of graphic that I was heavily inspired from. I essentially just recreated it in code in Python and generated samples and plotted it. Yeah. But yeah, so the left-hand side is homogeneous CLWE, the right-hand side is standard Gaussian. And the intuition I want to take away from this picture is that it's really hard to know which case you're in unless you're looking at it from the exact right direction. If you look at it from the exact right direction, then you can see this discrete lattice-like structure, but otherwise it's just as good as it looks like a Gaussian. At least that's the intuition. And as the dimension increases, there are going to be exponentially many possible directions you might need to look at. So good luck finding the one where you can observe this discrete structure. Okay, so now let's finish up the claim about CLWE implying hardness of learning mixtures of Gaussians, even this density estimation problem. It's improper learnable. So what's the sketch of the proof? The sketch of the proof is that, well, first there's a reduction from CLWE to hCLWE. And this reduction is effectively going to be rejection sampling that I described. You're essentially only going to keep the samples that are close to 0 mod 1. And this will exactly translate you to this decisional hCLWE problem that I've defined. And now I have to argue there's a reduction from hCLWE to learning mixtures of Gaussians, even in an improper sense. And what's the idea here? The idea is that, well, this distribution is a mixture of Gaussians. And well, a single just standard Gaussian is sort of trivially a mixture of Gaussians. So in either case, you're gonna be able to get a good density estimate from whatever distribution you're in. And then given this density estimate, you can perform a basic statistical test to distinguish between which case you're in. And doing this, you can distinguish you can solve the decisional hCLWE problem, and then you could solve CLWE. That's the high level idea of this group.
So if you have, if these were really circuits that were estimating the density function, like the simplest thing you could possibly think is like in a small region around the origin, is there a point that has low density, like where the PDF is small? That's not true in a standard Gaussian, but that's true. Like
Sure.
But that's hard.
Yeah, that would be hard.
You can do something standard.
Yeah, so the rough idea, if I'm remembering correctly, is you take Gaussian samples. So you just generate a Gaussian sample and feed it into your density function. For a standard Gaussian, this will probably be pretty high, but with high probability for the CLW, it's going to be pretty low, because you're probably going to hit one of those holes. Yeah, that's what it looks like. Okay, so what do our results say for this problem? Or rather, okay, let me start with what's known. So BRST show that under the quantum worst case hardness of certain lattice problems, it's hard to learn roughly square root of n Gaussian components in the mixture. And where does this square root of n come from? The reason for this is that they show that CLWE is hard only for gamma at least square root of n. And remember, gamma is the number of Gaussian components because they're spaced out like roughly 1 over gamma apart from each other. So this is going to correspond to root n Gaussian components. What we show is that under the polynomial hardness of learning with X assumption, you can bring this down to n to the epsilon. And this version of LWE can even be based on the classical worst case hardness of lattice assumptions. And furthermore, if you want to stretch it even more, assuming a sub-exponential hardness of LWE, you can bring this down to log of n to the 1 plus epsilon Gaussian components. And recall that, and the reason we can do this is that our reduction from LWE is going to allow us to show hardness of CLWE for a much broader range of parameters. For gamma, much less than square root of n. And so the number of Gaussians is going to be appropriately correspondingly reduced. And recall that the best algorithms for learning mixtures of Gaussians in polynomial time can only handle a constant number of Gaussian components. So previously the gap was square root of n to constant, and we bring this down assuming sub-exponential hardness of LWE to like poly log n or log of n to the 1 plus epsilon. Okay, you're saying, is there a reduction from distinguishing the Gaussian to LWE? Okay. Since LWE and CLWE are more or less the same, I'll just say for now, the same thing as asking whether distinguishing Gaussians reduces to CLWE. I don't think a reduction is known. I haven't thought about it. Yeah, I mean, yeah, certainly not in general. I mean, like for general mixtures of Gaussians, it seems very hard to translate it back to this lattice sort of structure. But for these particular instances, there might be hope for a reduction. Yeah. And so, as usual, there are two ways to interpret a reduction. Sort of the cryptographic or complexity theoretic way to interpret this reduction is that, okay, well, we believe LWE is sub-exponentially hard. And so as a result, we can now say that there's no efficient mixture to learn Gaussians for log of n to the 1 plus epsilon Gaussian. Alternatively, you could think of this algorithmically. Maybe you're very bullish on learning algorithms, and you think there should be some algorithm that learns G Gaussians in time polynomial in n and sub-exponential number of Gaussian components. If so, then you get a sub-exponential time algorithm for LWE, which would be devastating to ongoing standardization efforts for lattice-based crypto, and this would certainly be shocking to the crypto community. Okay, let me switch gears now and talk about how we actually prove this reduction from LWE to CLWE. So let's remind ourselves how these things are defined. So LWE on the right-hand side, left-hand side, CLWE on the right-hand side. The secrets come from different distributions, and the A sub I vectors come from different distributions, but everything else is syntactically exactly the same. Okay, so what we're going to do is we're going to convert samples from LWE into CLWE, and we're going to do it by transforming things a little bit by little bit in a series of transformations. Okay, our first step is going to be to convert these sample or these secret vectors over ZQ to the n into binary vectors. And for this, I'll assume the binary means plus or minus 1. So plus or minus 1 to the n. And the reason we can do this is, LWE has a lot of machinery, and using leakage resilience properties of LWE, you can essentially switch to roughly any secret distribution as long as the entropy is high enough. And so here, there's going to be a little bit of a blow up in dimension, essentially just preserving the entropy of the secrets. So it's going to blow up by a log Q factor, but for this presentation, I'll just ignore that for now. But really, one can ask for more. And instead of just binary, what if we make it sparse? So that by sparse here, I mean there are going to be k non-zero entries, and each of these non-zero entries are going to be plus or minus 1, let's say. So that's what I mean by the implication of intersecting with like the zero ball, sparse ball of exactly k non-zero entries. Well, it turns out we show you can do exactly the same sort of things from leakage resilient cryptography as long as you preserve the entropy of the secret distribution. And the benefit here is that the norm of this secret is now going to be like the L2 norm is going to be square root of k instead of square root of n. So in the binary case, the norm of the secret would be square root of n. Here it's square root of k for any k that we like, as long as you scale the dimension n up appropriately. Okay, so what's the next step? So we've made for now, let me just assume the secrets are binary, but in your head, you can think of the secrets as even being from a sparse lower norm distribution, and everything else that I say will also go through. So now our goal is going to be to convert these samples that are discrete, uniform over ZQ to the n to now from a continuous Gaussian samples. The first step in doing this is converting these discrete uniform samples, A sub I, into continuous uniform samples, A sub I. And to do this, we're just going to smooth by adding a very small Gaussian noise to these discrete values to make them continuous uniform. And the noise will also become some. And the second step, or sorry, I should say that the reason this works is because we've now fixed the oh, sorry.
I'm just using this notation.
Ah,
Is that a Gaussian or is that?
sorry. Yeah, I'm a little bit sloppy with it. So this is a uniform. So I think everything is uniform except for this.
Okay, so at the bottom also AI.
Yes, that's right. Sorry. Yeah, all the distributions are uniform, discrete, or continuous appropriately, except for the. Or maybe hCLWE, that might show up later too. Hopefully it's clear what that means. And yeah, the reason this reduction works is because the norm on the secret vector is small and fixed, and so the noise blow up is not going to be too big, and we're not going to get any leakage on the secret vector S. And then the second step of the second idea is to get this step to work is that we're going to sample like Gaussian A tilde i's that are going to be equivalent to the given continuous uniform A sub I model. So like we're given some sample, or we're given some vector A sub I mod 1 that's uniform, and our goal is going to be to compute some like Gaussian A tilde I, such that this Gaussian and this continuous uniform are equivalent to mod 1. So like the marginal distribution of these A tilde i's will be Gaussian, but subject to the constraint that it's given that it's equal to A tilde I, or sorry, equivalent to AI mod 1. And if you plug this in, is exactly what you want. In what sense? Oh, okay.
When you take mod 1, you're gonna
Yeah.
If it's by the
Yeah, I'm hiding a lot here. Yeah, so I'm blowing up a Gauss. I'm blowing up the Gaussian.
fluid nominal.
Yeah. I see. Yeah, I mean, so yeah, we make the Gaussian wider, and we argue in TV distance it'll be quite small. But yeah, I guess throughout this reduction we're working with real numbers. In the sure. Sure. I guess fair enough.
Yeah, I guess this should enter the idea of 1.
Yes, yes, that's right. What am I trying to say? But yeah, I mean, we're certainly only comparing we're only computing TV distances between continuous and continuous, and discrete and discrete, or we're never comparing TV between discrete and continuous. Certainly. But yeah, we do stretch out the width of this Gaussian here to make this work. So this tilde hides like root log n or polylog factors more generally.
Add small continuous Gaussian.
That's right. Yeah. Okay, and we're essentially almost done now. These A sub I vectors are going to be from multivariate Gaussian that are, standard, maybe slightly bigger standard deviation, but who cares about that for now? The secrets come from plus or minus 1 to the n, or maybe some k-sparse binary version. And you want to reduce it to one that's, uniform over the whole sphere of norm gamma. And for this, we use an idea of Brunner, Regge, Song, and Tang. We're just going to be to apply a random rotation matrix to your vectors A sub I. This is going to have the effect of re-randomizing your secret to be R times S. So no matter what your secret was beforehand, you're now re-randomizing it over the whole sphere of radius, the norm of the original secret vector that you started with. And in the binary setting, this is going to be the norm of your secret is square root of n. So we could just set gamma to be roughly square root of n. Or, in the sparse setting, if you want to stretch it, this gamma is once again going to be the norm of the secret, but the norm of the secret is now roughly square root of k. This is going to be, k could be much less than n. And so our gamma now And gamma in our reduction is going to be much smaller. Yeah, so this is the end of the reduction. We're now fully reduced from LWE to CLWE. Let me switch gears a bit and talk about some of the other applications of CLWE. So one is with one that I mentioned earlier on neural networks, on learning neural networks. In particular, Song, Zadok, and Bruno show that CLWE implies that it's hard to learn single periodic neurons. In general, it's known that it's NP hard to learn neural networks in the worst case, but maybe for neural networks, you're more concerned about the average case. And in particular, we're going to consider neural networks where you're given standard Gaussian samples. So X is from multivariate Gaussian, mean 0, covariance matrix, the identity. And we're going to consider functions of the following form. So like f of x indexed by some secret vector s is going to be cosine of the inner product of your input x with this secret vector s, where we're going to think of x as being average case Gaussian, and the secret is going to be just like in CLWE, it's going to be scaled up unit ball or ball of radius gamma. And this function is really like a very simple neural network. Why is this a neural network? Well, you're applying some linear function on your input x, and then you're applying some nonlinear activation function to it. So this is like a single periodic neuron. So a very simple example of a neural network. And what SCV show is that CLWE implies that it's hard to learn this function f sub s given like noisy samples. So if you're given like Gaussian x sub I and noisy outputs of f, and for some arbitrary small noise, it's going to be hard to learn this function. So it's hard to learn these single periodic neural networks. And what's the proof? I hope I can fit it mostly just in a slide here. The proof is just going to be apply cosine to this like a noisy inner product mod 1 of these CLWE samples. So remember that these CLWE samples look like a noisy inner product in mod 1. When you apply cosine of it to it, two things happen. The first thing that happens is that this mod 1 term goes away because cosine is periodic. So mod 1, who cares? You can get rid of it. And second of all, this because cosine is Lipschitz, this noise E sub I will grow maybe into some slightly bigger noise E sub I, but it's not going to be too much bigger. And this is just going to be exactly a noisy output of this function f. So by taking these CLWE samples and applying this cosine function, you exactly get input-output pairs of this noisy neural network. Okay, great. And so to interpret this, I haven't really talked about like how gamma plays into this result. But really, if you want to like normalize the weights of your neural network to be of unit norm, that as gamma is really a frequency of the activation function. You can pull this gamma factor out, and it's just going to go into the frequency of this activation. So you're going to have some really, really high frequency thing if you imply BRST. So the BRST show the gamma hardness for gamma at least root n. And okay, that's great. But if you use our reduction, you can bring this down to gamma equal to log of n to the 1 plus epsilon for small epsilon. And you can interpret this as saying for even much less frequent activation functions, this is still going to be hard to learn. And more than that, our reduction actually reduced the sparse secret vectors if you just skip the step of re-randomizing over the sphere. And so you even get hardness of learning sparse small frequencies, or like small frequencies and then sparse weights in the neural network. Okay, now let me switch gears and talk about another application, which is backdoors in machine learning models. And let me try to motivate the setup here of this problem. Let's say you're a scientist, you have some data, but you don't have enough data to train this model yourself, or rather you don't have enough computation power to compute such a model yourself. So what you might do is you might pass this on to some AWS or something like this to train your model for you. So you're going to give the data to the cloud, and this cloud is going to give you some trained classifier. In this case, let's say we're considering just classification. What this paper is concerned about is, what if you have a malicious model training server, like a malicious AWS server provider, that somehow gives like a backdoored classifier. And what do I mean by a backdoored classifier? So I'm going to say there's a backdoor if for every point x, one can generate a slightly perturbed x prime. It's like x prime near x, such that the classification of x and x prime are different, so the exact opposite of each other. So this is their notion of what they consider a backdoor. And we say this backdoor is undetectable if the honest and the backdoored classifiers are computationally indistinguishable. And what I really mean here is like the AWS is giving you a full description of the classifier, like randomness, everything. They give you a white box description. And even given this white box description, you can't distinguish between an honest version of the model, which has no backdoor, and the backdoored one.
Is the adversary also?
Let's say in this example, yes, they can. Well, yes, they're computationally bounded, but they have enough computational power to train the model, whereas the scientist doesn't, for example. But yeah.
Well, I'm just wondering, like, if the adversary is also just emulate the adversary to try and find the
Oh, so the adversary is not going to try to find an x prime. It's going to have some efficient way of generating x prime.
that doesn't need to be learned from that.
Yes. I'll give it next slide. But yeah, the way the adversary is going to plant a backdoor is going to be very efficient. Yeah. And okay, so the theorem statement is that assuming CLWE, one can essentially do this. One can undetectably plant backdoors in what are called random Fourier features classification models. Oh, be there yet? So in supervised learning, a popular classification method is to use the linear classifiers over random features of it. So let's say you randomly sample some feature map from some distribution. That's going to take your input and get some real number. And then you're randomly going to learn, or you're going to learn the weights of a linear classifier given these random feature maps. So like your classifier is going to be the sign of like linear combination of these random samples, random feature maps. And your goal is to learn the best fitting weights A sub I. One particular paradigm of this is the random Fourier features model, which has some nice theoretical properties. But the distribution of feature maps that they consider are as follows. So these phi sub I are going to take your input x. It's going to output the inner product of x with some Gaussian vector, WI, where WI is a standard Gaussian in dimension n. And then it's going to add some random phase, v sub I, then it's going to the cosine. So the randomness of these features are first in the random vector W from a multivariate Gaussian, and the random phase v sub I. Yeah, does this make sense? Okay, so now let me give the backdoor strategy. And I claim it's not too complicated. The backdoor strategy is going to be, well, instead of sampling WI from a Gaussian, sample WI from the hCLWE distribution. Except technically I'm going to have it be shifted by a half, so that instead of WI prime and S being roughly 0 mod 1, we're going to make it roughly a half mod 1. You can still do the rejection sampling in pretty much the same way. But yes, this is like a shifted version of the hCLWE distribution that I mentioned earlier. And now once you have this, the backdoor strategy is just going to be, given input x, my x prime is going to be x plus the secret vector. That's going to be the nearby point that has the opposite classification. And why is this true? The point is because, or what's going to happen in the cosine is that you're going to get an extra term of WI prime inner product S. And we know it's going to be roughly a half mod 1. And the cosine kills the mod 1, and it's roughly a half. So it's going to flip the phase of this cosine. And so the sign is going to be flipped for any of these random feature maps. And so by linearity for f of x prime is going to be the opposite sign. So we've now flipped the sign of the classification just by adding this the secret vector. And moreover, it's indistinguishable from the honest one because all we've changed about the distribution is just where the randomness is coming from. Instead of from a Gaussian, it's now going to be from a hCLWE, and that's it. So in fact, like the backdoor strategy is really just run the honest training algorithm, just have a different source of randomness for it. And what's the interpretation for this? Like, how close are these backdoored points? Well, these backdoored points, x prime minus x is exactly the secret vector. And the L2 norm of the secret vector is exactly gamma. So gamma exactly characterizes how small these perturbations are that the adversary can backdoor undetectably. And BRST give gamma equal to square root of n. We can set this assuming sub-exponential hardness of LWE, so it's a log of n to log of subset. And these perturbations are going to be much smaller. And more than that, we showed that you can make these by a reduction. These secret vectors S can be sparse, so these perturbations can actually be sparse and small perturbations. Okay, so let me conclude there and just give some open questions. So we should, can you extend the results to show hardness of sublogarithmically many Gaussian components? And if you can, are lattice reductions and lattice problems really the right place to start? Are they the right place to look? Another question you can ask is, can you build like better or new cryptography starting from CLWE instead of LWE? And you might complain and say, wait a minute, well, I've just tried to argue that CLWE and LWE are equivalent. We already know cryptography from LWE, so why even ask this question? But the point is that maybe the starting point of CLWE enables you to think of constructions and primitives that you might not have thought of if you just started from LWE directly. And lastly, are there other connections between learning problems and CLWE? And I think certainly the answer to this is yes. And the question is, which ones are they? Are they all connected in some sort of web? Say an analogy with like planted clique in similar problems. And I guess, what is the landscape of these average case high dimensional statistics problems, and what are the connections between them? Okay, thanks so much. That's all I have.